Hello everyone, this is 2.5 on the chain rule, and I will remark that the chain rule is probably the most important idea in the entire course. So, let's say we're looking at this function here. You can see that I've blocked off the work. It's not really so important that you follow through, but here is some work that shows how we can find the derivative using our limit definition, and we end up with this in yellow. Okay, the the point here is that this work involved with the limit definition is like way too much work, and the author here says, all right, there has to be a better way. Okay, so there is. The better way involves a recognition of what function composition is all about, because there is a rule that's coming up called the chain rule, which we will also refer to as the composition rule. We use it whenever we have a composition of functions. So this function h right here is an example of a composition of functions. We have here that h of x equals the square root of something, where that something is not just x, it's something else other than x. So we can think of it as this, so the way they've written it right here is this function called g. So g of something equals square root of that thing. What we are putting into g is this function f. So if we put this guy into here, we have that. This should be a review. You should have gone over the composition of functions in Algebra 2, in pre-calculus. That doesn't necessarily mean you understand it, so please feel free to come in to see me at office hours. But I'll talk very briefly about what is meant by this composition notation. So this is read g of f of x. We read it from right to left. That means that the inner function is f of x, and the outer function is g of x. So if we think about our kind of analogy of a function machine, every function has an input and an output. So let's say this first function right here is called f. So we put something into the function, call that x. We do some algebraic work here according to the right-hand side, right? According to the rule of f. So in this case, with the function on the left, we have this rule. And what comes out is some number, right, called f of x. We can chain this together. That's why we use the word chain rule. We can chain this function together with another function, and this one's going to have a name, right? This function is g. We can also give this f of x a different name, y, because over here, this function was in terms of y. So g of y says just take the square root of your input. Okay. And then what comes out is this number called g of y. So what I want to pay attention to is right here. Let's be a little bit more careful about that line. This thing could be called the output of f, or it could be the input to g. Right? This thing that comes out right here is coming out of f and into g. So we have chained these two functions together. Something comes into here, something happens, it gets spit out, something happens, and then it comes out again. This is the composition of functions. So we can also I think we will draw another diagram. So we have this set right here, which is the domain of f. Here is the range or the set of outputs of f. This function that goes from here to here is called f. We take in an x and we spit out something called f of x. We give that a new name called y. That y becomes the input to the function g. The output over here is called g of y. So if I want to do this kind of in one step, we have this new function, which is called g composed with f of x. In purple, this is the name of the composed function. We can write this as g of f of x. This means the output of the function f is what gets put into the function g. A couple different ways of symbolizing it there. So, anytime we have the composition of functions, we need the composition rule. We need the composition or the chain rule, just two names for the same rule, when we want to find derivatives. So we have this new designation here. Z equals the square root of y, and y is x squared plus 1. So another way to write z of x is going to be, well, we take the square root of something. What is that something? X squared plus 1. So if I want the derivative of this function, let's first find the derivative of this, right? Let's find the derivative of z with respect to y. That means treat y as the independent variable, just like x. So the square root, the derivative of the square root is 1 over 2 square root. Now let's look at this one. The derivative of that with respect to x is going to be 2x. So we have these two component derivatives. Now we have here this z equals square root of x squared plus 1. Now this equation right here, it's not exactly multiplying fractions because the definition of these symbols is a little bit complex, but without making it too complicated, this is a way that we can think about this chain rule. It is not the case that these are going to like cancel, but you can kind of think of it that way as starting with z, going through y and ending up with x. This is my chain. Okay? I start with z and take derivatives until I end up with just x. This is my chain. So, we have this guy here, dz dx, starting with z, going through y, ending up with x. This is my chain. So the chain rule is always going to involve multiplying things together. We have this first guy here, which is 1 over 2 root y. Then we're multiplying that by 2x, which was dy dx. And so we get this guy right here. Canceling those 2's, we have this. So we have x over square root of x squared plus 1, which is what the notes got using the limit definition. Understanding all the details might be a little bit beyond the scope of this course, but we got to be able to actually do problems involving the chain rule. So we're just going to do a bunch of practice. And we'll begin that after stating the actual chain rule. So let f and g be differentiable functions. That means you can take the derivative and define big F of x equals f composed with g of x. This is just the name for the composition of functions. Okay, so now the derivative of big F of x is going to be, let's label this. This thing in pink here is the derivative of the outer function with the original input times the derivative of the inner function. And you can call this the chain rule or the composition rule. I kind of like calling it the composition rule because we remember that we need to use this rule whenever we have a composition of functions. So here's an explanation in words. The derivative of a composite function is the derivative of the outer function times the derivative of the inner function. So let's practice that a bunch. So we're being asked to find the derivative for each of these. Okay, y equals sine of x squared. Notice that the input to this sine function is not just x. So here is one thing that might be helpful for you. We can rewrite this as y equals sine of something. So the derivative is going to be the derivative of this guy times the derivative of the inside. So the derivative of sine is cosine. And now I just need to find the derivative of the inside. So at this point, I just plug in x squared. So I've got cosine of x squared times the derivative of x squared. So we have cosine of x squared times 2x. That's using this substitution here of some other letter if you like. We can also do that without the substitution. We can kind of just do it straight away. So I know that y prime is going to be the derivative of the outside function, which is going to be cosine, with the same input. So I'll write that down. This is the derivative of the outer function with the same input, right? We're not changing the input at all. We started off with x squared, and so we'll keep it there. We started off with x squared, so we'll keep it there. Times the derivative of this guy. So I take this one, and it needs to be multiplied here, but I need to find the derivative. This is the derivative of the inner function. Couple more practices here. So like we did today in class, the meaning of sine squared of x is sine of x squared. So the function that we're looking at is something squared. The outer function is the squaring function. So that means we're going to take the derivative of the outside function, which is 2 times the inside to the power of 1, right, using the power rule. We're going to keep the same input. Now we're going to multiply by the derivative of the inside. So this is the derivative of the outer function, and this is the derivative of the inner function. So just to be clear, we have 2 times sine times cosine. We will rewrite this one. Anytime you have a radical, you can rewrite that, as a fractional exponent. I'm going to do some color coding here. Remember, the square root is so common that we don't write the 2 out front, but the square root is the same thing as the 1/2 power. So this function has 3 layers. We have the inside, we have the middle, and we have the outside. So we're going to basically be multiplying derivatives until we get all the way to the inside. So derivative of the outside, we're going to bring that 1/2 down, right? Because it's something to the 1/2. So 1/2 times something to the 1/2 minus 1. The inside's going to stay the same. Okay, times the derivative of the inside. My inside function is secant of something. The derivative of secant is secant times tangent. And we keep the same input. Now we've got to multiply by the derivative of this inside function. This is the innermost layer. So we're going to multiply by 3x squared. So you can leave your, well, I guess we can simplify further. Okay, so we have 1/2 times secant of x cubed to the negative 1/2 times secant of x cubed times tangent of x cubed times 3x squared. So this is secant and so is this. So I've got negative 1/2 and a 1 right here. So negative 1/2 plus 1 is going to be 1/2. So I can write this as square root of secant of x cubed times tangent of x cubed. And then I've got my 3/2 x squared. 3/2 x squared. Okay, now this is some pure nonsense. This is way too much work. Don't worry about that example. Okay, more stuff to come.